team number 66 of Operating Systems Lab. Our topic is Deadlock and Concurrency Algorithms website. We had to make a website entailing various algorithms that could be used to avoid deadlock or concurrency in an operating system. We have implemented 8 algorithms ranging from MuteX to the banker's algorithm. The team 66 contains of 4 members. I am Ashay Panchal, the team leader, and I was supported by my friends and my fellow members Aryan Patel, Astha Modi and Bhavya Shah. So I'm going to show all the 8 algorithms of deadlock and concurrency. The first one is MuteX. MuteX is an algorithm that ensures mutual exclusion of processes, which says that only one process can execute its critical section at a moment. If a process is completing its critical section, all other processes would have to wait until the previous process completes its critical section, as it is seen here. P2 has to wait until P1 completes its critical section, and so on. Here is the process log, which shows that the number of processes that are completed or are in critical section. This process avoids deadlock while it ensures mutual exclusion, bounded waiting and progress log. We can reset the algorithm and go back to the home page. The next one is counting semaphore. It asks us the number of processes. Let's just enter 5. So the 5 processes are represented. Since the semaphore value is 3, at a moment 3 processes can enter the critical section and complete the critical section simultaneously. Other processes would have to wait in queue. So once a process's critical section is completed, another process takes its place, as is shown from the animation. Here also the process log is shown. Since multiple processes can enter the critical section at a moment, mutual exclusion is not followed, and so isn't bounded waiting. We can reset and change the number of processes and go back to the home page. The third one is producer and consumer. So the producer and consumer is a problem when the producer produces the number of chunks and they have to wait until the consumer consumes it. So we can change the producer chunks and the queue capacity. Now see, if the queue is full, back pressure is obtained and the producer has to pause before producing the next chunk until the consumer consumes the previous chunk. We can change the queue capacity and also change the speed from which the producer produces the chunks and the consumer consumes them. We can set it from fast to slow, slow to fast, or even random. We go back to the home page. The fourth algorithm is lock variable. Lock variable does not ensure mutual exclusion, which means if that 2 or more processes can complete their critical section simultaneously, as it is seen from the animation. But it ensures that deadlock doesn't occur, and it also gives bounded. It also doesn't give bounded waiting and gives a progress log. We go back to the home page. The fifth algorithm is binary semaphore. Binary semaphore means the value of the semaphore can only change from 1 or 0. So when the value of semaphore is 1, the process can enter the critical section, and when the process is executing the critical section, the value of semaphore changes to 0. So all other processes would have to wait. Once the process exits the critical section, it is completed and the value of semaphore is changed. So all other processes can continue to complete their critical section. Since the semaphore value can only range from 0 and 1, mutual exclusion and bounded waiting are ensured in this algorithm. This algorithm also avoids deadlock. We complete the process and then go back to the home page. The sixth algorithm is Petersons Solution for concurrent programming. So this is only applicable for 2 processes. It ensures that mutual exclusion is done between the processes. For example, a process is having a critical task, so another process would not be able to access that critical task unless and until the previous process completes it. We can reset the algorithm and go back to the home page. The next one is test and set lock. We enter the number of processes. This algorithm also ensures mutual exclusion, that is, only one process can enter the critical section at a moment. But the bounded waiting is not accepted by this process. That means a previous process can be executed before the one that has come earlier than it. But deadlock is avoided by this algorithm, as is our goal. The process log of all the processes are shown here. Our final algorithm is the banker's algorithm. It is for resource allocation and deadlock avoidance. We have 5 processes and 4 resources. So once we start the algorithm, we get the claim vector of all the 5 processes for the resources, and the allocated resource table for each processes, and the maximum resources that are available for each process. Once the algorithm completes, we are given output that shows the safe sequence for the execution of each and every process. So in many cases the safe sequence is not obtained, which makes the process in a deadlock condition. Here in our resources and processes, the deadlock is avoided and a safe sequence is obtained. Thank you for bearing with us during this presentation, and we hope you enjoyed it.